Hey folks, my name is Dionne. I work at Apple and I maintain Libc++. So this talk is going to be about lit and some of the recent work that has gone into it to make Libc++ easier to test and its test suite more flexible as well. So let's get started. So first, I'm going to give an introduction to lit, and I'm gonna introduce some of the concepts behind lit for people who might not be familiar with the tool. Then I'm going to explain the Libc++ testing format, which basically is the link between the test suite and lit itself, which is just a test runner. Then I'm going to give some usage examples of the new Libc++ test format. And finally, I'm going to close with some improvements that we've made to lit as part of this work. So lit is the LLVM integrated tester. It's essentially a test runner that is used everywhere in LLVM. I believe all the projects are using it. It is possible that some do not, but most projects are definitely using lit as a test runner. And when I say a test runner, I mean that it really is just running the tests. It's not defining what the tests are. It's really just like a cradle to run the tests if you want. It is also a standalone tool that can be used outside of LLVM, but I haven't seen it used that much outside of LLVM. And it is a simple Python code base. It's an LLVM utils. I found it really easy to hack on, and you just submit a fabricator review, and the folks working on lit are going to respond. So it's really nice just to hack on the tool. So the basic usage of lit is to call lit with giving it some test suites, and test suites are basically just directories containing tests. Okay, and so when you're using something like ninja check all, basically what happens under the hood is that we are calling lit with a bunch of test suites. So we'll say the Libc++ test suite, the Clang test suite, and so on, right? And then passing a bunch of options, of course. And here, notice that I am omitting, a little bit of complexity. In reality, we're not using lit, we're using LLVM lit. It's not really important to understand the difference at this point. So the way lit works is really simple. It's a general kind of workflow, if you want. So basically, lit starts by discovering the test suites. So it does that by looking at the folders that you passed it and looking for files called lit.cfg or lit.site.cfg. So when it finds a file like that, it's going to assume that it's a configuration file to configure the test suite. So it's then going to load that file and run it as a Python file. So you can have arbitrary Python code in there. And basically lit has this config object that is available in the config file. And that's what you should use to specify what configuration options. You'll see an example later. And then once the test suite is configured, it's going to discover the tests by traversing the folder that you provided it, and it's going to create basically a programmatic representation, like a Python object representation of each test. And then it's going to use a test format to run the tests, to run like each test in order. So lit really works as, it doesn't really specify how to run the test. It specifies everything around that. So it's going to handle things like reporting of the test failures and successes. It's going to handle, for example, parallelism. It's going to run, all your tests at the same time. Well, up to some number, and stuff like that. But it does not really define what you're testing and how you're doing that. And so in the config file, you need to specify a few things like the name of the test suite and also the folder where you should actually discover your tests. So that's the folder that contains the tests. And then you also specify the interesting part here, which is the test format. So here we're using ShTest, for example, which is the most, I think, widely used test format with lit. And so ShTest is basically a test format that interprets test files as containing shell commands that can be run and that represents basically the running of that test. So like I said, the test format is essentially just a Python class with an execute method. So when lit discovers the test, it then creates a Python object representation of each test. And then it's going to call the execute method of your test format on each test, right? So the test format only has to specify how to run a single test. And then lit is going to do that, maybe 20 cores at a time and so on. And then your test format should basically return a test result code. So there's a few test result codes like, for passing, failing. If a test is not supported, for example, you could have a test that is not supported in a given environment or on a given system. Then there's xfail, which means basically that the test was expected to fail and it failed, which is basically a type of success result code. And then there's xpass, which is the opposite of that, where basically you were expecting the test to fail, but it passed unexpectedly. And then there's timeout, which is obviously for a test that times out. So for example, the ShTest format is pretty simple. So you can have special annotation in your test file. And so unsupported here, for example, means that the test is going to be considered unsupported if we're on some system. And then the run lines are the really interesting parts. So essentially, lit will parse the run lines as shell commands, and it's going to execute each line individually. And then if any of the lines of these commands basically returns a failure error code, then the test as a whole is considered to fail. Right, so here we're just running clang, %s. So %s is what we call a substitution. I'll get into that later, but basically it gets expanded to the current file name. And so we're running clang on the current file and producing, an executable a.out, which we're then running on the second line. So if either the compilation or the execution of the executable fails, then the test as a whole is considered a failure. Right, so like I said, basically ShTest just parses some special markup in your file and then performs substitutions, which I'm going to get into right next, and then it executes the run lines as shell commands. And that's nicely packaged in this execute ShTest function. So you can build your own test formats with lit and reuse execute ShTest if you want. It's really convenient to do that. So about substitutions, basically the config file can contain a list of substitutions. These substitutions are just tokens that are going to be expended in your run lines. So for example, if I'm using %clang somewhere in a run line, instead, first lit is going to parse the run line, and then it's going to look for occurrences of %clang. And then it's going to replace that by whether I put in my config file here. And that's really convenient. Say you want to test the tip of trunk clang that has just been built, then you can't really say user bin clang because that's not the one that was just built. So you really need some kind of substitution there. And so what you can do is basically put the path to your just built clang, ask lit to substitute %clang for that, and then you're good to go, right? And that's actually what we do in LLVM. It's just that the %clang, actually the whole config file is generated by CMake, because CMake knows where the just built clang is going to be. So you can have custom substitutions, but there are also several built-in ones, and they're really useful. So there's like %s, which we just talked about. Then there's %S, which is essentially the directory name of the current file. And then there's %t, which is basically a unique name associated to the current test. So that's really useful if you want to create something like a temporary executable or just a temporary file to say you're compiling an executable, then you could say like %t.x. That would be the name of your executable, and that's just a temporary executable. It's not going to collide with anything else. So then you can run that if you want, for example. So there's a bunch of other substitutions. They're all documented. So with that background, now we can understand a slightly more realistic example, like this one, which is taken from some Clang tests. So here we're basically running Clang CC1. So lit is going to expand that to the path to Clang and then dash CC1, then a bunch of options, and then %s, which expands to the current file. And then we pipe that into file check. So just skip the file check. It's completely another topic. But if you concentrate on the first part, basically the interesting bit here is that we're really running the just built Clang with these options, and we're passing as the current file as an input to Clang itself. But because the run lines are commented out, Clang is just going to ignore those and then compile the file. So it's a really nice and really terse way of running tests, really. And everything is nicely self-contained in that single file, which is great. Okay, so the old libc++ test format was kind of complicated. It was all bootstrapped in Python. So when you called execute, it would basically launch the compiler and then produce a binary, and then it would run the binary. But there's a lot of stuff you have to kind of to care about if you're going to do that. Like you want to make sure that you handle timeouts correctly. You want to make sure that so you need to pass sometimes like standard input, for example, to the executable you're trying to run, and that gets pretty complicated pretty quickly. So there was a lot of complexity around that, and it wasn't super flexible as a result, right? So instead what we did is refactor it, and obviously here I'm simplifying everything to make it look really good. The new test format is quite complicated as well, but the principle is different. Now, basically what we do is we match the file name, we look at the suffix, and depending on the suffix, we do something different, and which we already did before. But the way we do it now is we basically just run a shell script. We consider all the tests in libc++ to be shell tests, but we inject specific commands at the front of that shell test, right? And so that allows us, so we assume here, let's take a look at the compile that failed at CPP, right? So that file, that sort of test should fail to compile, right? So what we want to do is just run the compiler with -f syntax only, and then if that failed, then the test is considered a success. So one way of doing that is just say, hey, let's pretend that that is a shell test where the run line is, as we can see here, it's just running cxx with the proper flags and with -f syntax only, and then negating that result, right? So then we call execute shell test with these preamble commands, which are basically commands that we can inject at the beginning of a shell script. And so that's pretty simple. So we make the assumption here that somehow the cxx, the flags, and the compile flags substitutions are made available to us. That's kind of the assumption we're making. But given these substitutions, it's really simple to express what we want. So similarly, we can create a .verify.cpp test, which basically runs Clang with Clang verify, right? And then a pass.cpp test is, again, just creating an executable by running the compiler and then executing the executable. So %exec is just another substitution that we expect is able to run some executable. And it is useful to have this substitution because, as we'll see later on, we might not want to just run the executable. We might want to, maybe run it on a different device or something like that. Right. So it is really simple in that kind of paradigm. It is really simple to support new kinds of tests. So the new test format supports all different kinds of tests. So it has the pass.cpp, which should compile, link, and run. It has the run.fail.cpp, which should compile and link successfully, but it should fail to run. Otherwise, it's considered a failure. And then same for link.pass.cpp, so it should compile and link, but we never run it. And then it should be able to compile but not link. That's a link.fail.cpp. And then we have compile.pass.cpp, compile.fail.cpp. And the two last ones are pretty interesting. So the shell.cpp, from our point of view, is just a no-op really, because it's just whatever commands are already in the file. So that's basically a true shell test. It's just a raw shell test where we don't have anything to run in addition to what's already in the file. So that's just a normal shell test. And then there's a verified.cpp, which we already saw before. So the configuration required for this, for the new test format, is basically the basic configuration plus some substitutions like we saw before. So you need to pass the %cxx substitution, which is the compiler to use for compiling the tests. Then the flags substitution is flags that are common to compiling and linking. And then there's the compile flags, which are just the compilation flags, the link flags, which are just the linker flags, and then %exec, which is basically a script that should be able to run an executable, which by default basically should be just run.py, which simply executes the file, right here, right there on this machine. The format itself also defines some sugar definition substitutions, like %build, which just builds an executable, and run, which executes the just built executable. So that can be useful if you want to run, for example, %build and then add some flags, for example. So this gives us a lot of flexibility. For example, we can run a test against the static library, against statically built libraries, which is super convenient. And it's super easy to do that. You just need to change the linker flags to link against the .a instead of using the dilibs, right? Or the .sos. Another thing we can do is run the test on a remote device. So this example is taken from from one of the LLVM build bots, which is a cross-compiling bot from Windows to Linux. So you just specify the right target, and then you link statically. And finally, you use ssh.py, which essentially this executor will just copy the executable that it's trying to run to the host and then run it through SSH on the given host. So that all works out pretty nicely. And of course, an extension of that is running the test suite against another standard library. So for example, this here is running the test suite against libc.c++. So you just specify that GCC is your compiler, and if that's a tip of trunk GCC, it's just going to use the tip of trunk libc.c++. So it all just works out nicely as well. So the interesting ideas in the new libc++ test format are really that we're reusing shell tests for most of the logic. So before, we would write everything from scratch, and that made stuff quite a bit more complicated. But now we're basically using the shell test for most of the logic there. So we don't have anything to do. So I think that's definitely saving us a lot of trouble. Another thing is to really consider substitutions as inputs of the test format. So substitutions can be seen as some kind of variables that are kind of parameterizing the test format, and seeing them that way makes us use them in ways that we might not have thought before. And so that was definitely one of the big factors in making the new test format easier. And finally, the idea of building substitutions on top of others wasn't possible before. Now it is. But for example, defining person build as the expansion of other substitutions allows us to create more complex substitutions on top of others, which can be quite useful as well. And so this solved a bunch of problems for us. For example, the configuration files used to be really complicated, and now they're a lot more straightforward because they're a lower level. So you control directly what flags you're passing to the compiler. There isn't like 10 layers of abstraction between how the test is being run and how you're specifying the configuration file. Now it's basically you're specifying exactly how you want the file to be run, whereas before the configuration was just a lot more complicated. And also, because the new configuration file is a lot lower level, you control directly what you want to do. It means that we can handle a bunch of funky use cases that we couldn't before. So for example, people wanting to run the test against a statically linked libc++, or against a statically linked libunwind, they can all do that really easily now by just passing the right flags, creating their simple config file. Whereas before, it would have required adding new knobs basically to the big configuration object we had, and doing that actually required stringing these options through CMake, because the configuration file was configured via CMake. And so we'd end up with like a bunch of options in our CMake that whose only goal really were to tweak how the test would be run, which I think is wrong, because really what we want to do instead is just allow CMake to decide which configuration file to use for running the test suite, and then that configuration file can be as complex as it needs to be without actually having an impact on the CMake itself, which should really be just like how to build libc++ as simply as possible. So I'm really looking forward to cleaning up some of the older CMake stuff when this gets more wider adoption. So in order to make all of this possible, there were a few improvements to lit. So first of all, we had to add flaky tests in lit. So please don't use that. Flaky tests are not really great, but for libc++, it was sometimes necessary to run tests more than once. For example, in the case of some threading tests or some timing dependent tests. So now at least it's not ad hoc, it's well supported in lit. There are also recursive substitutions. So like I said before, nowadays you can have a substitution which expands to other substitutions, and they're going to be expanded recursively, whereas before it wasn't quite true. So some of that would work, but it was really kind of ad hoc the way it worked. So there are still improvements to be made here, but it kind of works. We also added an option called show used features, which allows you to list all the features used in a test suite. So like used in the unsupported annotations or in the exfil or requires annotations. So using this, you can easily find out like old and unused annotations. And so, for example, if we see something like, if I see an annotation for like client 3.5 here, which we do not support anymore, I can go ahead and clean up the tests that are using client 3.5 by removing these annotations. But also, I might find out that there are some workarounds for this compiler, and that allows me to keep my my test suite pretty tidy, which is quite nice. So I have been able to clean up a lot of the libc++ tests that way over the past few months. And finally, like I said before, previously it wasn't possible to pass arbitrary commands to ShTest. It would just read whatever is in the file. But the preamble commands parameter was added, and now you can pass basically arbitrary commands to inject at the beginning of the ShTest, which is useful for authoring custom test formats on top of the ShTest format. So that's a tiny improvement, but that is quite powerful. So that's pretty much it. I hope you enjoy, and thank you.
Hello, I'm Michael, and I'm here with Louis. I'd like to thank everyone for watching. And we have a few questions. I'll start with the first one. So someone asks, I love Lit, but documentation is missing lots of stuff. Any plans to improve it?
So I'm not aware of any plans to improve it, to be honest. So I think it's well, I think it would be useful to understand exactly what parts of Lit you think are undocumented. I've personally found it pretty well documented, and I've documented the changes that I've made to it. I Yeah, I think, but apart from that, I don't think there's any specific effort going on about improving the documentation for Lit. If if you can show us some areas that are not so well documented, then I'm sure I or other Lit people would be happy to improve that.
Okay, and the next question. Do the changes presented in this talk, are the changes available in this talk available for other libraries? If not, are there any plans to enhance generic Lit with similar functionality?
So the changes presented in this talk are in basically two categories, if you will. So the first category is basically improvements to Lit itself, which are by definition basically basically just in the Lit program, so they're available anywhere. The other bigger part of the changes is in the implementation of the libc++ testing format. That testing format is currently checked into the libc++ repository. And so it's not technically available for testing other libraries. However, it would be possible definitely to productize that testing format and to basically make it available or reusable, in say compiler RT or other projects that require the same kind of testing. I guess we could also make the libc++, we could probably make it a little bit more generic and then include it as one of the default provided testing formats in Lit. If that is the sense of the question, then I think it might be possible. It would require a little bit of work, but it could be pretty interesting and add a lot of value to Lit for sure. I'll think about that.
We have, I think, one more question. Can you override default substitutions in config files?
No, you cannot. I had not thought about that. No, you cannot, because they are set a lot later in a lot after you actually parse the config file. So you cannot right now. I would be curious to see what the use case for doing that is, but if there is a valid use case, then this is probably something we could look into doing, actually. I think I know how to do that. We could just avoid providing the default substitution X if X is already part of the substitutions, which I think is pretty easy to do. But I would be curious to understand what the use case is.
Okay, well, I think that's the questions we had. I think thank Lee for the talk and everyone for watching.
Thank you.